Thank you very much for that, Ms. Gray. You saw me way down the wicket, and I got stumped just now, eh? All right. So, current relays. Now, we may have mentioned the whole business of unit protection. You know, you're looking at a specific point or a specific component within your protection system. The overcurrent relay, we use that primarily for non-unit single point relay. So it gives coverage in many instances, not just to a single device, but it may give coverage to a section of your power network. All right. By themselves, the relays monitor the measured power system current, or the current flowing through a particular point in our network. Yes. And in order to get full coverage, there is need for what we refer to as coordination. Now, what does that really mean? Within our network, we are going to have transformers, yes? We have generators at different points. It therefore stands to reason that you will have different magnitudes of current passing through different points on the network. Similarly, when you have a fault, the fault current flowing through the system is going to be different depending on where in the network you are located. And you would have seen that from your last lab. Yeah, you look at different points on the network depending on whether you are looking, the side of the transformer you're looking. We don't really need to go into all of that. But the bottom line is you have those differences. So it means, therefore, that if you have overcurrent relays within the system and we want to achieve what we would have spoken about some time ago, which is discrimination, you want to ensure that only the right part or right portion of the circuit is removed from service. And when I say right portion, I mean that portion that is under fault, right? The fact that we have fault current passing through a particular point in the network doesn't necessarily mean that it is under fault. You with me? Because the fault current needs to pass through certain parts of the network in order to get to the fault point. So to ensure proper discrimination, to ensure that only the faulted section is removed, we go through this exercise when using overcurrent relays known as coordination. Okay? Now, there are three basic types, and we mentioned them last week, right? So in terms of their operation, we have instantaneous, we have definite time, and we have overcurrent relays, which carries an inverse characteristic. So for the instantaneous, it simply means that once the current exceeds a particular value, then we are going to have operation. All right. For the definite time, again, once it exceeds the preset value, then it gives a specified time within which or after which it will operate. And then finally, for the inverse characteristics or the inverse relays, as the current increases, the operating time is reduced. Okay? So our main focus this afternoon into this evening will be on the inverse relays. And for your inverse relays, right, obviously they have the greatest utility in our power systems, right? So you'll find them used mostly in our power systems. The others are usually in industrial settings, eh? But for your power system, of course, as the current increases, you want the operation time or operating time of your relay to be reduced. And in terms of the name that is applied, I just mentioned inverse characteristics, but the proper name is the inverse definite minimum time, or IDMT relay. Okay? And I just chose that photo. It's not necessarily that that is an IDMT. Yeah? So in terms of the systems of protection, as I mentioned, the instantaneous and definite time are used with your IDMT and auto-reclose schemes for feeders. And by feeders, we are now moving from the transmission to the distribution side of things. But although I make the statement, I still want to underline the fact that in terms of use within the power system, what you are going to see is primarily inverse relays. All right? All right. So the inverse relays, we further delineate the characteristics by those inverse characteristics by identifying 3 types. Yep. Now, you do have some further variations, but in terms of the 3 standards under your inverse relays, you're going to have your standard inverse, you're going to have your very inverse, and you have your extremely inverse characteristics. As I said, and I think I've highlighted it here, that it's not limited just to these 3, but these 3 are what we would say are, at the forefront. So standard inverse, very inverse, and extremely inverse. And in terms of please let me know if I'm going too fast. Right? In terms of the characteristics, this is what they would look like. All right. So you have your standard inverse, and note that they are starting at the same point. So they have the same starting point, but the characteristics differ significantly. So you have your standard inverse up top, then the very, and then the extremely inverse. What we have also done is to superimpose the characteristic of the fuse on it. And you will see that for the fuse, let's take a little bit touch for this thing. Yeah. That's not what I want. Anyway, I'll figure it out very soon, don't worry. Yeah, so the characteristics are shown. Yeah. The fuse is superimposed because one of the things we will note later on is that the extremely inverse is usually used in networks or parts of the network that you have fuses as part of the protection system. So where you have fuses and you are also going to be using relays, then you would use the extremely inverse. And as I mentioned at the beginning, the whole activity of coordination, okay, will require that you're going to use characteristics that are close together, because that will reduce the challenge or the difficulties associated with coordination. So let's just recap what we said so far. 1, the overcurrent relays, you have them as instantaneous, you have definite time, and you have inverse relays. Good. The inverse relays, refer to them as IDMT, That's your inverse definite minimum time. And then for your inverse relays, the characteristics we just mentioned, you have very inverse, standard inverse, and extremely inverse. All right? Any questions so far? Any comments? Anything you want me to clarify before I go any further? No? All right. Now, for your static relay, the characteristics that I just showed, yes, they are derived empirically. So, you know, these characteristics for your electromechanical, yeah, you would be getting it from experimental data based on the design of the relays. Good. However, when we now start dealing with static relays, the approach is a little different. So those curves that I just showed you, which you would have gotten with the electromechanical, these curves are now derived using equations. So for your standard inverse, that's the equation. All right. So we have 0.14 T, 0.14 times T over IF divided by PIN to the 0.02 minus 1. And that gives you the operating time of the relay. So the operating time for your standard 0.14 T I of IF over PIN to the 0.02 minus 1. And we'll define this, you know what? So why we're not taking notes, Mr. Duncan?
Sure, I'm taking notes. That's not showing on the screen.
Pardon?
I'm saying that's not showing on the camera, sir. I'm taking notes.
Okay. All right, and finish with that. For the very inverse, we have 13.5 T divided by IF over P times IN minus 1. So for this one, you have the IF over PIN is raised to the power 1. 13.5 T. And then for the extremely inverse, we have 80 T over IF divided by PIN squared minus 1. So for your static relays, this is how we define our curves. So the characteristics that you get, right, are derived from these equations. All right. Now, by way of definition of these variables that you see there, IF will be the fault current as seen by the relay. Now, you can either consider this in terms of what is happening on the primary side or the secondary side of the CT. So you can look at it in terms of what's on the system vis-a-vis what's on the secondary side of the relay. oh, sorry, the secondary side of the CT. It will work out to be the same. So IN there would be the nominal setting, nominal relay current, relay operating current. Big T, time multiplier, and P is the plug scale multiplier, or the relay's setting current. In fairness, PIN would really give it a plug setting. So, so it will be IF over IN. So that would really give it a multiplier. Are you with me? So when we call here the plug scale multiplier, that's a sort of old term, because we now know that we can get the plug setting directly from the relay. So we know the operating current of the relay. So what the denominator is really giving you, right? What we're getting here would really be the plug setting, right? And so IF over PIN would be giving you the multiplier in terms of what you are seeing during the fault. But I'm giving you the PIN because the example that we uses would require that information. But don't get too thrown off by it. All right. So in terms of the relay types that we'll be looking at, yeah. So we have that for your analog, or not, well, for your electromechanical, we derive those. All right. And then for your static, we use the formula. Okay. Now, just to make a few more comments regarding the three inverse characteristics. We have here we are showing the saturation curves in terms of the relay, CT output to the relay, right? So that's saturation CT with your standard, your vary, and your extremely inverse characteristics. Where are we mentioning this? And you have the diagram, right? So just make a note that you reference that particular diagram. So for your standard inverse, your standard inverse is going to show what we refer to as appreciable tolerance to CT saturation. So where you're running the risk of having your CTs saturated, the standard inverse relay, we'll treat with it. For your vary inverse, use the feeder protection. It allows you to have an operating time which is proportional to the distance of the fault position. So we talk now about a feeder, because the feeder, primarily radial feeders would have a source point. And that source point really is with respect to the call it a transformer, because you're not really going to be connected into a generator at a feeder. So a feeder would be coming from a substation. So it's really a transformer point that you're looking at. So you are then, as you go along that feeder, what you're doing is moving further and further away from the source. You see? And if you're moving away from the source, then it means that you're going to have increased resistance, and therefore the current flow will change. And also the fault current that you're going to experience along the feeder will change as you move away from the source. Okay? So your very inverse, those characteristics provides for use on feeders. And with the extremely inverse, as I mentioned before, because their characteristics are so close, where you have systems, yes, that you have fuses as part of that protection architecture, that's where you're going to find the use of your extremely inverse relays. Now, we have made 2 attempts so far to show you kind of up close what your overcurrent relay looks like. And quite frankly, this doesn't I mean, it just, the picture I'm about to show really just highlights the fact that it is an electromechanical relay. We will try our best to show that it's really an overcurrent, but anyway. So I believe this is by far the best photo I have of your electromechanical. All right, did you finish writing this up? All right. So I think this is the best photo I've had so far. All right. Even though it's still not that good, but we work with it. So we have our disk. Yeah. Let me see if let me jump to the other one, because I think that one may look a little bit. I'll come back to it. So if you look at the top, again, I don't know if you had seen it in the previous attempts I made, but up here, can you see the dial up there? So is that dial right at the top?
Yes, sir.
All right. And that is what you would turn in order to get the time setting. And remember what we said is that in shifting that dial, all you're doing is moving the movable contact closer to the fixed contact. So the movable contact, which is, oh Lord, boy, they have their benefits and their faults. It's difficult to see the movable contact. But anyway, it is fixed. If you look right here, right? You can see the shaft that it is on. And so the movable contact is fixed onto that. When you turn the dial, you're shifting it closer to the fixed contact. It's difficult to see. You really need to come into the lab. So next you come into Kingston, we'll go into the lab and I can show you this up front and personal, all right? You plan to come to Kingston and or are you all in? I'm sure I asked you this question already. You know. Who is in Kingston? Nobody? Portmore?
Closer, Portmore. All
right. Anyway, if you decide to come by UTEC, you can, whenever you come, we can go down the lab and I'll show it to you. Anyway, this is what it looks like. Let me go back to the point though. We already said it, so it's nothing new. We know that the electromechanical works like the watt-hour meter. The larger the current, the faster the disk is going to turn, right? Which is this. Oops. All right, so you have the disk, which is going to turn much faster the higher the current. These are those braking magnets to prevent overshoot. All right, the contacts are in here. Okay. So you higher the current, the faster it moves, which is why the inverse relationship. All right. And obviously, the faster it moves, the quicker it will operate. So, key students. When we are setting our overcurrent relay, there are only two values we are looking for. And I think we have already spoken about that. We're going to give the current setting, which we already know, the top setting. Yeah? And we're going to give a time setting. Now, so far, whether in power systems or in the discussion that I've had in protection, so far, I've only told you about the current setting, and we have looked on the curves with those top settings, the time dial settings, right? That's all we have done so far. What we are going to do this afternoon is to take it one step further. Rather than me saying to you, well, the time setting is 0.5 or 1 or 2, we're going to go through an exercise to see how exactly we determine those values, which time setting we are going to put it on. All right, so we're going to go through an exercise which, you know, we'll highlight how that is done. All right? We're good so far? Well, I tell you, you know,
Yes,
I like you guys, but at the same time, I don't like you all. You know, too quiet, man. I don't want you to work for chatting, you know, but yeah, you know, you're all too quiet, man. Yeah. And that's not because I go to a noisy church. But anyway, let's move on. So in terms of your block diagram, yep, sorry, this is what it would look like. You have your plug block, right? Your plug block, and depending on which one of these you put the plug in, and it's a physical plug. It is a metal plug that you actually unscrew and then screw it into one of those boards. All right? So that's how we call it plug. So in terms of what we do, what we use, we get the name plug. Yeah? In terms of what it is doing physically, what it is doing is tapping off a portion of the winding. That's why we also call it the tap setting, because it's tapping off the winding. You with me? So it's plug or tap. And then of course here's your rotating disc and your magnets and you name it, right? So this is what the electromechanical looks like. So the basic principle, whether or not I'm using electromechanical or static relays, the basic principle remains. I must be able to define the curve, and the curve is going to be defined for the electromechanical in terms of empirical data. Or, as we will see in a few minutes, well, we did say earlier, for the static, we define it using the curves, the equations. So in terms of the static, the question is, what technology am I going to use to define the curves? All right. For the electromechanical, we know based on the the design parameters, etc., we can derive empirically what the curves will be. For your static, the question is, how do we represent the mathematical formulae that I showed you earlier? So the current setting for your relay, yes, is known as the plug scale multiplier. So that's one way of referring to it. But of course, the plug scale multiplier times the nominal current really gives you the tap current or the plug current. All right? And then the time setting is your time multiplier setting. That's a big T. So these are the two numbers. These are the two values that we are going to need to determine for our overcurrent relay. Once we know that, then we set them, the system operates, and based on the settings that we have, it will discriminate as we wish, and that comes through coordination. All right? Now, in terms of your overcurrent relay, and we mentioned this last week or the week before when we're looking at the evaluation of your CT. We said that for your electromechanical, it has a very high burden, and the burden changes depending on the amount of current that is flowing to it. All right? The electromechanical relay, it derives power from the power system itself, and therefore operates with a very high burden. All right? So it has a very high burden. The example I'm about to show you, I'm the first to admit it's quite convenient. Yes? But anyway, you will get the picture. So if we have an overcurrent relay, there's a burden of 1 VA at the setting current. All right, so at the setting current, we have 1 volt ampere. If we assume the input impedance to be constant, then the burden at 10 times the setting current is going to be equal to I squared over ZS. Now, if we then see a current which is 10 times the setting current. So if we then have an input current which is 10 times the setting current, we then have a burden of 100 VA. And based on what we looked at a couple weeks ago, where we showed that the burden, yes, the relay burden, which is going to add to the overall or put additional strain on the CT, has the potential of raising, whether it is VGH or VEF, but it has the potential of causing our CTs to saturate. So we have to take that into consideration when using electromechanical. And quite frankly, I mean, I should confess, you're hardly going to find many of these in industry today, but we still have a duty to let you know that because you're going to find that industrial facility which uses these types of relays. And whether you are tasked with transitioning or facilitating their continued use, you at least have some passing knowledge of them. So in terms of the impact, as I said, we have shown that by looking at that example of assessing the operation of your CT. All right. Okay, so next we talk about static relays. So we have just dealt with the electromechanical, and we have been talking about it quite a bit. Yes, a lot of what I have said, I know it's repeated material. Now we want to move to your static relays. So under static, we want to start firstly by referencing your analog relays. And these relays would use your transistor, your op-amp circuits. Okay? Now, when we compare the static relays, the analog relays, to your electromechanical, okay, we see that the static relays have some benefits. Low burden, improved curve repeatability, obviously, because with your electromechanical, although you would have gotten the characteristics, or you would have derived the particular characteristic empirically, it would have been under certain operating conditions, including temperature, pressure. Yeah. If those change, then the possibility of you getting slight deviation from the expected curve, that may occur. It may not be significant, but it still occurs. So with your analog, you will have a greater chance of improved curve repeatability. Reduced frequency errors, less susceptible to temperature, as I mentioned before. And of course, it makes the relay smaller. So when you look at well, that kind of unfair, let me not use that. But earlier I showed you there's a static relay, nice and cute. But then when you come to the electromagnetic, they are quite bulky, very bulky. So that's one benefit of your analog relays. So it allowed the size of the relay to be reduced. All right. If you go into many of the substations within our utility company, you'll see a lot of space in the relay rack. As a matter of fact, in many instances, or in some instances, rather than leaving the space, they just leave the whole relay, even though it isn't doing anything. So it's there. Because the newer relays, what you would have needed 3 electromechanical, you now use 1, which is monitoring all 3 phases. You had an electromechanical per phase. Yeah. So those are some of the benefits. On the flip side, obvious reasons, the analog will be more expensive. Whilst the electromechanical derived its operating power from the system, which in of itself can be seen as a drawback. All right? Because you would need the provision of I was gonna make a foolish statement, because even though you need the station transformer, you still will need it for the analog, because those will be used to maintain your batteries. Right? So in addition to the analog being more expensive, needing the battery bank, they're also less robust for obvious reasons. Yeah. You know how easy it is to destroy a transistor radio, right? As against the one that your grandfather had. And if he's still alive, still has. Huh? But I know I'm shooting over your head, but you know, we did have radios with tubes, but you know, moving right along and doing so rather quickly. So this is what your analog would look like. And note the distinction where we say we are using op amps. So you have this figure. Right? We're using op amps, we are using transistors. Good. So you know, we have our input circuit from our CT. Yeah. And then we have our loading resistor. We have our curve shaping circuits. Yes. And by that, we're talking about integrators, differentiators, all of that fancy jazz. Yep. You have your ICs. Of course, you have to power all of that. Okay. And then over here is where you now have the contacts. So the actual fault current doesn't flow through the relay. All right. So the contacts, which then closes your circuit for you to trigger or to operate your circuit breaker. Okay. So basic structure of your analog relay. All right. Key difference with what we're going to be talking about in a few is that for this relay, you are using transistors and that whole technology. All right. That's the basic difference. But so remember, we spoke about the two settings, your plug setting and your time setting. All right. So your time setting would have been provided there. And the plug setting, this is the loading resistor that we're talking about. Let's see if I can erase this thing. Finally I get it. All right. Good. So your plug setting will be based on that. Right? That's what we would adjust for your analog. And then for your time setting, you know, it's internal in terms of the decision-making circuit. Okay, so we have now spoken about the electromechanical, and yes, we have done that several times. And now we're talking about the analog. The last thing I want to mention about the analog is that, and I spoke to it just now, in terms of the contacts external to the relay, right? Which energize your trip circuit for your breaker. Right? So the last thing we mentioned there. So it uses that hinged armature, which provides isolated output contacts. So you're going to find these mainly in a factory setting. They are good enough. And at one point in time, as a matter of fact, many of these relays, when they came into the current utility, they didn't last very long. So they came in and went very quickly because they were replaced by what is now there, which are your digital relays. All right. And it could very well be because we didn't start changing all the older meters until in the 90s, 2000. Right? So by then, persons were now using digital, so the analog didn't last very long. Okay. So thirdly, we don't know about the digital relays. Right? And you know, as you'd expect, we are now dealing with chips, microprocessors, yeah. And in the same way we have your curve shaping circuits. With these mini computers in terms of the microprocessors, we are now able to hold the curve data in them. The benefit of that is that with my digital relay, I can now select whether or not I want to use a standard inverse, a very inverse, or an extremely inverse on the same device. If I was using a standard inverse for my electromechanical, I would have to change out the relays if I were using extremely before. But now, if I want to, I can buy one set of relays, and if I want extremely, or if I want standard, yeah, I can make the selection. Okay? A lot more robust than the analog. I can't speak, well, you know, maybe it was just a matter of money at the time because, you know, JPSCo really didn't start getting capitalized in a meaningful way until in the 1990s, right? Which is when the government gave up the majority of its shares, right? And then you start having private capital coming in. That's when all this change and, you know, started to occur. So it could very well just be a matter of money, why, you know, that transition through the analog didn't occur. But when you go there and start working, you let me know. All right. So in terms of the operation you have here on the microprocessor, that will now have your curve information. That's where you would hold your time setting. So after you have done your calculation, you'll be selecting your time setting. And this may not necessarily be a push button thing. Yes, you'd actually have to connect this up to your computer and just load it. Yep, load on the information. Your plug setting, you're just selecting one. Now I'm showing it here as physical, but as I said, you would use your parallel port and connect and, you know, shoot the information in. So all the calculations you would have done that at the office, and you walk out with your computer, connect it to the relay, upload the information, and as they say, we call that George. All right. Any questions? Am I going too slow?
You're going at the correct speed, sir.
I know the possibility of me speeding up would have gotten you away. All right, so that worked. So we can move on. All right. Okay. So again, similar to the analog, the same mechanism is used for connecting to the power system. All right. All righty then. The current setting, we simply switch the values of the CT loading resistance, which we showed here. All right. So that's your plug setting. We just switch one, and depending on how many you have in parallel, then you would get the current that would be required, a change in the current that would be required to operate your relay. Your time setting is just a matter of selecting. Your curve setting, a matter of selecting. So again, in terms of capital cost, it may be a little more expensive, but in terms of the operational flexibility, it will be worth it. All right. And as I mentioned before, it's not, although I show it as switching, it is not necessarily a physical selection, but rather uploading of the data to the relay. All right. So you have, as I mentioned, the selectable curves. You have all three available. We have already spoken about the burden advantage, whether it is the analog or the digital, it doesn't matter, right? Just as good. We require this separate power supply. So of course, you'd still have to get information or have an appreciation of battery maintenance. And I hold up my hand and declare that I am one power engineer who needs to go do some work on battery technology. All right. I am horrible where that is concerned. But anyway, I'll get there. Or I'll just continue to buy the service. All right. Okay. So we want to know jumping and sort of jumping with both feet in looking at how we go about setting your overcurrent relay. What do we do? What is this thing we talk about grading? Right? And at the core, it's just that we want to make the selection that will protect our system first and foremost, but it will also allow for this word that I think it is now part of your DNA. It will allow for discrimination, right? And that activity that we are going to get into is known as grading. So we're going to look at a grading exercise. How do I go about setting some relays to ensure that I get the discrimination? And by the way, this is something that you will have to do. That's why I'm teaching it so early. Okay, it's gonna come up in your lab. It's gonna come up in your project. All right. So you'll have to make these settings. All right. So we're gonna go through the grading exercise. Now we can apply it to any configuration. Of course, as the configuration changes, the task, of grading becomes a little more difficult. When you reach utility, they will go through their steps in terms of grading. But for now, I'm going to just introduce you to a very simple system, simple radial system. All right, in terms of the calculations. So here's the system, and you already have it. Yeah. Now it's obviously it's not clearly shown, but you have a great supply point. And that grid supply point is not necessarily a generator. As I said, it could be a substation, which means that the supply would be coming from your transformers. All right? It's just that you are being supplied at a grid point. Whatever, well, obviously, coming off from a substation, which means that you're feeding off a transformer. What we have here, these bus bars, you can think of them as no communities. So let's see now. Let's say this feeder is running up Hope Road or Old Hope Road. So this would be going down to Mona. This one is heading up to Papine. Right. This one is heading up to Old Pastures. Yeah. So these are our load points. Right? And the relays here, so you have a relay that is, and all these relays are looking at what is happening down here. So A is looking down, B is looking down, etc. Or depending on who you want to consider it, maybe looking up, but it's looking down. All right. So this is the system we have. We have 4 relaying points, right, along the feeder. And the question is, how do I coordinate these relays to ensure that that when I have a fault down here, only this guy operates. Or if I have a fault here, this fellow operates. But at the same time, I want to ensure that if I have a fault here, and this fellow is supposed to operate, if he doesn't operate, I want to ensure that only B operates. So if B operates, then the person's connected here and here would still have power. Only, those beyond this point would lose power. You with me? So how do we separate the network? I know I'm showing circuit breakers here, right? But let's, just think of them as, I don't want to say fuses because obviously the type of relay that I'm going to be using, which are very inverse, you wouldn't be using them with fuses. But these are those switches that are connected to the relay that will open the circuit. All right? Okay, so that's our network. So for the exercise, and I've written them alternated them in red and blue because I want to be clear in your mind about this. Before you start a grading exercise, these are the things that you must have. You must have a single line diagram of the network that you're going to be looking at. 2, you must have the capacity of the source. So what is the source at that? What's the capacity of the source within the network? Thirdly, you want the symmetrical impedances. You want the plant impedances, symmetrical components. Now, tell you up front, you may not necessarily need to calculate anything else because you would have also had the you'd also have the modular system. So or even if you don't have the modular system, once you can sketch this thing and create your single line diagram, you throw it into a program and you do your fault analysis. Because you have been exposed to carrying out your fault analysis on the network. All right? Now we mentioned motor starting current and fault curves were applicable because on the fault, depending on the size of the motor and the type of the motor, they will contribute to your fault current. All right. And then finally, we also need the CT and the relay information. So we need a single line diagram. We need the source capacities. Yeah. We need the symmetrical components, plant impedances. Yeah. We need motor information. In other words, for the motor information, you'll be needing information for large manufacturers who may be along that feeder, because they may, under fault, contribute fault current. So you need to know if you have a bottling plant that is being fed by this feeder when you're doing your calculations. Right? And just a note, we have this. Just as a note, one, when you're using these relays, you want to use relays having the same characteristics. So you're not going to mix IDMT and not IDMT, very inverse and extremely inverse. It's not that it cannot be used. However, in terms of matching the curves, it makes life a lot easier. All right. It's not that it can't be done, just that your calculations will be, a lot simpler. And not that you're selecting based on the difficulty of the calculations that you need to carry out. Another point I want to make before we jump into the exercise. So in terms of the relays, you're not going to use the same relay to protect against phase fault as against earth fault. Because of course the settings are gonna be different. For your phase faults, you're gonna be using the 3-phase fault current. And so for your 3-phase fault current, even though we didn't do any such calculation, but you would have seen it in the lab. Yeah. For your 3-phase fault current, you're gonna need just the voltage and the positive sequence values. For your earth relay setting, you're going to need your single line to ground information, fault information, and so that would then be based on the voltage and your positive, negative, and zero sequence components. And of course, you are no experts on that. All right? So you don't need to worry too much about that. All right. This COVID thing is having an effect. I can't even stand up for half an hour anymore. I used to stand up for 2 hours and I'm fine. Gravity is now having an effect. But anyway. Can I move on?
Give me a second, please, sir.
All right, let me just take the upper. All right. So remember we spoke about discrimination, right? And this is just, well, keep in mind that we have already said this, we have already spoken about this. You want to ensure that the current setting is such, yes, that it is above maximum load, while at the same time below minimum fault current. So it must be above load or below minimum fault current. The other point that we want to make is that the impact of this is to ensure that the relay that is furthest from the grid has the most sensitive setting. And you will see that, you'll see why. Well, let me not make it a mystery. The further it is away from the grid, obviously it means that during fault it would see the lowest current. Yes? And because it is seeing the lowest current, then it means that the sensitivity of that relay would be highest. Right? Now, I know exactly what we have been saying to you in power systems. And so the next point, I know will raise some eyebrows, but nothing to worry about. All right. So the rule of thumb I'm going to give you. In terms of our setting, we said that we would have used, the plug setting, we wanted it just above the load. And, when we're doing the assessment or the evaluation of our CT selection, we gave you certain percentages, or in terms of the selection, we worked out the percentage above load. All right? So as a general rule, we want to ensure that the relay current is greater than twice the load current. And this has its advantages. Yeah? It has its advantages. Among them, during maintenance, depending on the bus bar arrangement that you have, you may need to shift load, within the system. So you shift load from one transformer to the next while you're doing, switching operations. Now, you wouldn't want the system to then shut down simply because you have transferred load. So this sort of criterion allows you to carry out certain activities without disruption. All right? And at the same time, you want to ensure that it is less than half the minimum fault current. Now, the issue is, and I note, I have put it in red. All right? So I still have blue. I've put it in red because what you will actually select It's going to be a compromise between the two, as you will see. So although I give it as the rule, what you want to ensure is that the load current will not result in the relay operating. And if you are exceeding load current, remember we're talking now about utilities. It's not at home where, and even at home you still have a little time if your circuit is overloaded. You still have a little time to make adjustment. So the key here, the key objective is that you want your system to operate, not to operate under load current. All right. So, go to the example. Any questions on this? I can move on. All right.
No questions.
Yeah. Go ahead.
I would say no questions.
Okay. All right. Now, did I send you the question in the in Schoology? I hope I did. I hope it was in the.
Yes, sir.
Okay, good. All right. So we have an 11 kV system, and obviously at that voltage we're dealing with a distribution. Yeah. And obviously, we know we operate at 24 in Jamaica, but the point I'm making is that it's a distribution line. And the task for us is to choose the current settings for the inverse relay. Yes, at the 4 locations. The source capacity can vary between 75 and 150 MVA. And the line impedance are shown in the diagram. So where we have the taps, to go into the various communities, we have a certain amount of impedance. And we want to assume that the relays have a nominal rating of 5 amperes. So the nominal current now would be, remember the formula that we gave you earlier, I nominal? Now we said that you can look at that nominal current on the system side, or meaning the network side, or you can look at it coming from the CT. All right, so it's either the primary side or the secondary side. We are giving it here on the secondary, but of course, if it's nominal 5 amperes on the secondary and you have a 100 to 5, then the nominal on the primary would be 100. Is that clear? So the nominal we are giving here is a nominal on the secondary of the CT. But in your case, and you'd agree that if I am dividing 5 million by 30,000, and I divide both the 5 million and the 30,000 by 20, I'm gonna get the same answer. So if I divide what is on the system by the turns ratio, I'm going to end up with the same final result as if I had converted it and then divided by only the 5. Anyway, don't worry about it. Don't worry about it. It's not that critical. But the nominal rating is 5 amperes. And this is on the secondary side, obviously. And the plug settings, note, in terms of what you have looked at so far with overcurrent relays, where you had tap settings, what you had were current values. Agreed? This time around, what I'm giving you, and it's no different, I'm just giving you percentages. So it will be percentages of the current settings that you have. So it is 50%, so it means that whatever the current is, it will be 0.5 of the current. Everybody with me? If it is 75%, it's 0.75. It's 200%, it's 2 times. So we're not changing what you already know in terms of your tap currents. So it's important that we understand that. Now, in terms of what we have up here, I mean, what do we mean by the capacity changes from 75 to 150? Remember, I explained that in terms of your feeder, that will be coming from a substation, which means that it is being fed by a transformer. Yeah? Agreed? So if the capacity can vary between 75 and 150, all we are saying is that that particular feeder can either have 275 MVA transformers supplying it or one. So there are instances where you have one or you will have two. So it's not that we're adding generation. It's the capacity that we have created or expanded. So coming into that bus bar, which would be your substation, you have a capacitor going out to the feeder of between 75 and 150. So you either have one transformer operating or you have two. Now, if I have two transformers operating, it means that the reactance would be halved when both are operating in parallel. Come on, man. When I see that sort of response from you, I start questioning whether or not you went through network. So I should be able to just set that and move on quickly. All right? So if we have two sources, these are voltage sources, think of them as ideal voltage sources. If I look at their equivalent reactance, it must be half when I have two of them in parallel. All right?
Yes,
so we just get that. So, you know, these things like to embarrass me. That's me. Oh, come on. Good. Let's get back to business. Good. So this is the network. So let's understand the network. So remember I told you about the communities. Or we say Papine, Hope Passes, etc. So think of these loads. As going into those communities. All right? So you have this, let's say that is Papine. This is Mona. This is Hope Pastures. Which other community nearby? Whatever. This is Ligani. All right. So those are our communities, and this is the feeder from the Hope substation. So that's Hope substation. Okay. These now represent the impedance between each point that I have tapped. So between the substation and Ligani, well, this is a bad example because we really should be going up the road. And feeder can spread in two directions. But you understand the concept, right? So we have the reactance, the impedance between each point. We have the relaying point. Here's my relay. And the CT that is supplying each of these relays. We are given those. So we have for D, 100 to 5, for C, 200 to 5, 400 to 5 for B, and 400 to 5 for A. And we want to know, first task was to determine just the current setting. So remember, how many settings do we need for your overcurrent relay? How many settings we need for the overcurrent?
Two, sir.
Two. All right, so we're going to start with the current setting. All right. So, did I give you this table?
Yes, sir.
Yes, sir.
Yes, all right. So let's now look at how we go about filling this out. And you're going to do some calculations so that you're comfortable with it. Up top, we talk about the in-zone impedance. Now look at where A is connected. All right. Now A will be right at that bus. And the minimum in-zone impedance from A that it would see would be, right at the tip, would be the impedance of the source. So for that point, when we get the 0.81, right, is that we calculate the impedance as per the two transformers connected in parallel. So the voltage there is 11K. So it's 11 squared over 150 MVA. And we get 0.8. It's not exactly 0.81, but this was, I wasn't very nice or keen on maintaining the standard as far as the decimal place is concerned. Right. So we have maximum capacity, which is the 150. We have the minimum in-zone impedance, which would be 11 squared over 150. So you just confirm that. Make sure my math's right. All right. And then for the max, since I have already rounded off for the 0.81, well, let me wait on you. Have you confirmed the 0.81?
Yes, sir.
Yes, sir.
All right, good. And for the max, because we have the denominator, so we are now going to go to 75, then obviously this would double to 1.62.
Excuse me, sir. Can you hear me?
Yeah, man.
My internet went as you explained the 0.81. You can repeat it, please.
That is with both transformers in place. So with them in parallel, the total MVA would be 150. And so the 0.81 would be V squared over S. So we get 11 squared over 150. That's how we get the 0.81. With a 1.62, that's with one transformer in, so it would now be 11 squared over 75. But we don't really need to work that out because we know this is at 150. So at 75, then it must double. So we get 1.62. So if we're now looking at the in-zone fault current, Remember now, we're still focusing on relay A, right? For the in-zone fault current, if we have the in-zone impedance, and in-zone fault current would be the voltage, which is 11 over root 3 divided by the 0.81. And that gives us our 7840. Which therefore gives us our 3920 for minimum. So the maximum would correspond to the minimum impedance. X, X, double X, double X. All right? All right, now, anybody, can you remind me as to why we need to go through a grading exercise? What did I say? What's the purpose of going through this grading exercise?
Sir, would that be to ensure that you have discrimination?
Absolutely. So if I'm going to look at relay A, which relay would it be providing backup for?
That would be to relay B.
All right, now, it therefore means that relay A must operate if relay B has a problem.
Yes, sir.
So in terms of the minimum fault, and by the way, well, you know what, before I go there, let's just finish the table. You can do the calculations on your time. All right. Any questions regarding those oh, come on, Zach. I tell him I finger them too big, you know. Where on this thing I need to do? Beautiful. In terms of relay A, everybody comfortable up to that point?
Yes, sir.
Now, let's look at the loads. So I'm going to look at the loads for each of these relays. If we go back to the network, all right, relay D, can we see that it will have 50 amperes? Are you comfortable with that? Relay C, what load current will it see and why?
We see 130, sir,
Why?
because it has to have the 80 at load right after C and then the one after D.
Okay, so it's carrying this community load and that community load. So that's how we get the 130. All right? Thank you, Mr. Buchanan. And also, if you go to B, it will now add the 170. So that's how we get the 300. All right? And then A would have to see all the loads. So the maximum load current would be 50, 130, 300, 420. We're good with that? I know it's kind of heavy tonight, you know, but you're creme de la creme, so let's move on, eh?
Sir, could you go at that one more time, please?
For the load currents?
Yes, sir.
All right, so here's your network. All right. Relay D must see 50 as its maximum load because the 50 amperes is feeding into that community. Remember, I named all of these as communities. So community D, C, B, A. You give them names, all right? This is the feeder coming from the substation. The 50 amperes in terms of maximum load must pass through D. For C, it must carry C and D as maximum load. So it must carry the community immediately after, and it must carry the community down the road. When we go to B, it must carry B, C, and D. So we have 130 plus 170 to give us 300. And then when we come to community A, or relay A, it must carry all 4 communities. All right? So that's how we get
Okay, sir.
the 50, 130, 300, 420. All right? We were already given the CT ratios, so we're not going to change that. All right? We're not going to change that. So if we now go back to our network, let's go back to the network. Remember the minimum in-zone fault. When we speak of minimum in-zone fault, the best way of thinking about it is what is the circumstance immediately in front of the relay. So when we calculated this 0.81, because the relay was situated at this point, we can remember, you know, the bus bar represents where the relay really is located, all right? But we can't draw it inside the bus bar, so we show it immediately in front. So if there was a fault right at the bus bar, right at the tip of the relay, right in front of the relay, the only reactance between the source and the relay would have been the transformers, which is why we just did that. Are you with me? So if I now go to relay B is on this bus bar. So relay B, the impedance immediately in front relay B must be the source plus the line. And so we go to our table. And in our table, we are getting 0.81 plus 0.6, which gives us 1.41. But are you comfortable with that? If not, say your piece. Similarly, if this is the maximum in zone for A, then we add the 0.6, we get the maximum in zone for B. And we continue. We add the 0.95 in order to get to C. And then we add the 2.2 in order to get to D. This is the minimum in zone and maximum in zone. Okay? So we have those reactances. And in order to get these currents, we're just going to be dividing the 11 over root 3 by each. So if you have the minimum in zone, At B, it will be 11 over root 3 divided by 1.41. All right? Minimum in zone, it will be 11 over root 3 divided by 4.56 and 5.37. Any questions? We good?
Yes, sir.
All right. Now, the next thing we need to determine in this table, the next thing we need to determine, now that we have all the fault and load information, remember we gave you the rule of thumb. We want half minimum fault, twice maximum load. Now, if I started with relay A, what is the smallest fault current that I want relay A to respond to?
So that we do 3,920.
That is the minimum in zone fault for A. But what do I want it to respond to? Remember, always keep in the back of your head, students, that the purpose of grading is to provide discrimination. So what's the smallest fault I want A to be able to respond to? Based on this table, which current would I want A to respond to be able to respond to?
Will that be the 420, sir?
No, man, but that is a load. That's a load current.
Sir, the 1,182.
Okay.
No, A, you know.
Sir, would be half of the 3,920.
All right. So I push you on this one. What's the purpose of this? You see, I'm repeating this because I want it to stick, eh? What's the purpose of grading? Talk to me, man.
Ensure that the right relay.
You're going to have to mute one of your devices.
Ensure
So
that
that-
the right relay operates. The correct relay
So
operates.
you want discrimination. And to get discrimination, A would play what role? And for what? What role would A need to play?
Well, A would need to ignore the faults that happen in the other locations. that
But
we
can it ignore it forever?
up to a certain
Which point? Up to what point should it ignore it?
Well, the maximum, the minimum fault here that A should operate is 3,920. So anything below that.
Note, you know, we didn't say anything about operation. You know, all I have calculated are the in-zone fault currents. All right. I know it's late, so let me work with it. Let me help you. A must provide backup for B. So in other words, ideally, if a fault occurs that B is required to clear, yeah, and it doesn't clear it, A is supposed to back it up. So the discrimination here occurs because in the normal course of things, A would ignore what is happening in B because you want B to operate when it has a fault. Agreed? But in the event B doesn't operate, you want A to clear the fault. Yes? And what you want is that B must operate when it has its minimum fault current. So you're going to choose a setting for A that will back up B when B is seeing its minimum current. So let me try to put that in. Well, I have put it in writing. So here it is. So it must provide backup for faults in the zone protected by B. It's not going to override B, you know. Yeah? But it will back up B. So it's setting. Remember we spoke about minimum fault current. So its setting is going to be based on what's happening with B. So it's half the B current, which is 1430, and twice its load current, which is 840. All right, now here's where the conundrum comes. Here's the conundrum. What are the available settings we have for the relay? From what to what?
In percentages,
Yeah, man. From what's the range?
50 to 200%.
50 to 200. Yeah? And what is the turns ratio of the CT at A?
400.
400 to 5.
Okay.
Now, based on the settings that I have there, what would then be the maximum that I can get in terms of the relay current, the relay setting current? Look at what we have just calculated. But you also are now restricted by what the relays are able to operate at. What's the maximum setting? What's the maximum percentage? 200. What's the CT setting? 400. So what's the maximum I can get from this?
So will it be 800?
800. All right? And therein lies, students, the beauty that I find in protection. It is not about you being able to do maths. All right? It's about you understanding what you're doing and making the compromise, which is what we have just done. So we have a relay. The relay gives us 200%, which means that the setting that we are going to make for A would be for a relay current of 800 amperes, which corresponds to the 200%. So I am restricted by what is available on my relay. Any questions?
Sorry, can you just run through that one more time? Just so
No problem. So what we are saying is that A, because this is the whole purpose of us doing the grading, to coordinate the relays so that they support each other. But you also want to ensure that only the relay which is protecting a particular area operates during a fault. So remember when you were looking at zones, you would have had this zone that covers the first part of the network. The zone that covers here, it would go all the way down. Yeah. So it will be overlapping that. And then that will be looking like that. All right? Good. In this case, however, we're not looking at anything in the reverse, so the overlap would only be going forward. So at A, we are saying that it must be able to operate in the event B does not operate for its smallest fault. If I didn't do that, students, if I didn't do that, look at what would happen. If I were to set A based on 3920, you realize how close 3920 is to the maximum fault at B? So if I had put it at 3920, B could have been experiencing a fault at 2860, yeah, or 3000, for example. Yes? Question, would that 3000 amperes be passing through A?
yes, sir.
Yes, sir.
But A's minimum fault is 3920. So it wouldn't have been providing much help to B. Because, you know, it hasn't even seen its minimum fault yet. So, big deal. You know, B is the one you're sweating, but who cares? So A must be set in such a way that it will respond, albeit slower. It must respond. Remember, I gave you that example with the fire truck or the fire stations. All of them see the fault, but only the one closest to the fault should extinguish the fire. So A will see the minimum fault at B. B would see the minimum fault at C. C would see the minimum fault at D. Where D is concerned, we now have to go to the end of the line, which would result in the minimum fault on the system. So all we would do at the end of the line is to now add that remainder that we didn't put in, which was the 1.1 ohm. And that's how we get the 491. All right. So let's go back to our table. So we have this. Do we have this?
Yes, sir.
All right. So the next table that you have is this. So the 1430 would be half the minimum fault at B, and the 840 would be twice the maximum load at A. And the compromise is 800 amperes, which represents 200%. At B, it's half the minimum fault at C and twice the maximum load at B. So we use a selection of 600, which corresponds to 150% of the 400 to 5. For C, it's a minimum fault current at D. So this would be B, so this C, and that's D, and twice the maximum load at C. All right, and for D, as I said before, we would simply be adding this, the 1.1 to the values here in order to get, well, to the value here in order to get the minimum fault. You with me? So this would be 982, I think. All right, and then C would correspond to that minimum current, because the minimum fault current would occur if I went to the end of the line. The minimum in-zone fault current would have occurred up here. But the minimum that it would see, that D would see, would occur at the end of the line, because it would now have to go through the additional 1.1. I know it's a lot to take in, but I want you to go through those tables that we looked at this evening, right? Go through the tables, and then when do we meet? It's tomorrow. Tomorrow when we meet, we have a discussion about it in the first part of the class, and then we look at how we go about doing the time setting, and that's it for your overcurrent relays.
Excuse me, sir. Hello?
Yes?
I can go back over one thing, sir.
Go ahead.
The 800 and the 200%. And just re-explain, because it seemed that we chose the 200% and then the 800, but then in re-explaining, it sounds like the 800 came first. And then because
all right. It is, since you put it that way, I'm gonna throw it back at you and say it's chicken and egg, all right? We have the setting here is 400 to 5. Agreed? The multiplier, remember I said that in terms of the plug setting multiplier that I have here, you can either look on the primary or the secondary side. All these currents that we're looking at here is on the primary. Good? So if we are setting based on the primary, we have it, we want it between 1430 and 840. But with a 400 to 5 CT, there is no such setting on the relay. So the only setting we have would be the 200% times the 2 times 4, which gives us 800 amperes. So the setting on the relay would be 800. Remember, I know the CT is fixed. And what we are doing in setting the relay is to find the current at which the relay will operate. And the settings I have are 200%, 150%, 100%, etc. Those are the settings I have. And I went as far, I think I stressed the point that what you have been exposed to thus far would just be the top currents, eh? So you would say this is a top setting. So you'd have selected a current value. This relay is giving you a multiplier. Well, the deafening silence feels like I have lost not just Mr. Johnson, but the whole crew.
No, sir. I get what you're saying, sir. The relay only has one set value, so the multiplier adjusts it. So it have the 400. So if we wanted to go to the 800, we have to choose the 200%
Just double it.
multiplier.
Yeah.
Yeah.
Go it over again. Spend a couple minutes with the record. Well, you're not going to get the recording right now because I'm going home. But yeah, I'll make it available. All right. And then tomorrow we look at the time setting. All right. Have a good one.
Sir.
Okay, sir, you too.
All right. Take care.